Anyway, I just want to introduce our speaker. Dr. John Hurdos is a research associate professor in the Department of Civil Engineering and is also director of the Minnesota Traffic Observatory. He's been working in the field for quite some time in ITS for traffic control and safety, traffic operations optimization, active traffic management systems, and certainly the work he's going to describe today has been going on for some time, and he's been working with Professor Gary Davis on a lot of the interesting projects that are going on in the MTO. I just want to also point out that he received this PhD here in the Civil Engineering Department back in 2005 and has been with us ever since. So without further ado, I'll let Dr. Hurdos get into the details of what he's been doing over the last up 10 years.
Is the microphone, you're working, okay. Good afternoon, everyone, and good afternoon to the people that are not physically here. I've been with you since 1994. I've been with you with a PhD since 2005. You know, I've been here for a very long time. And a lot of the work that we have been doing and a lot of work that I'm going to present you today has been supported by not just the Roadway Safety Institute, by the ITS Institute, which was the predecessor UTC before that, and it started supporting this research before UTCs actually existed officially. So it's a very long history that brought us to what you're going to hear today. A small outline of what I'm going to talk about. Just have one slide about the motivation behind the work that we've been doing, establishing a field laboratory on I-94. The background, it started in 2002. So it's been many, many years that this process have been evolving. How that laboratory, the original 94 field laboratory, has evolved, and it has also helped involve knowledge and practice, and how, and the subject of today's presentation is how it evolved to be a connected vehicle testbed, or has the foundation to be a connected vehicle testbed. And I'm going to share with you the system overview and architecture. And I'm going to finish with what is to happen in the next couple of years, because MnDOT has seen the value in some of the things that we're doing, and they actually are supporting continuation of this effort. So the motivation is known to all of us. Freeways are nothing but free most of the days, and there's congestion, and all of us, hopefully not with any element of surprise, we have to come to a stop. We have to join a queue on the freeway while we're going 60 miles an hour or more, in my case. So there's, apart from the congestion that we encounter every day, this surprise of meeting the queue, this surprise of changing the state of flow from uncongested to congested is what captures a lot of people unaware, and we have rear-end collisions and other even more severe crashes. These accidents, these crashes, are accounting for more than 50% of the congestion that we encounter on the freeway. So the rear ends are the dominant type of these crashes. So from early on, we were looking for ways to prevent them. Now, my work as a master's student in the University of Minnesota started in the developing systems for incident detection, because back in 94 all the way to 98, we did not believe we could actually prevent the crashes. So 100% of our effort was devoted in detecting them as soon as possible and doing the fastest and most efficient way of managing the incident so it can get out of the way and the road can start working as normal. Honestly, even in academia, there was no much dream of not making that crash happen at all, because they were considered as accidents. Accident implies an unavoidable event. It was around that time when the US DOT commissioner, or not commissioner, secretary, sorry, actually started a campaign saying not accidents, crashes. And he requested that we remove the word accident from our vocabulary because they can be prevented. We didn't know how then. There were cartoons of autonomous vehicles. There were ideas of vehicles talking with other vehicles. There were not even variable message signs changing dynamically, telling us anything. But the idea was that enough is enough. We need to prevent them. We cannot just focus on clearing them up. So we took that idea and we ran with it, as they say, and we were fortunate that a lot of people have been unfortunate very near us from here. I-94 westbound in downtown Minneapolis, and you can, all of you realize where this picture is from, has been for quite a long time now, and these statistics are from 2002, have been the highest crash location definitely on the freeway system of the Twin Cities, but in kind of frequencies pretty much unprecedented anywhere else. We are talking on a guarantee one crash every 2 days. So it was a perfect location to ask the question, are there any specific types of traffic? Are there any, other than individual human behavior, causal reasons for these things to happen? As I sometimes joke with my students, if we think that it's somebody's fault, then the only explanation for this location would be that there was a cone of stupidity that was covering this place, and anybody who enters it loses 90% of its IQ instantly. Because the statistics do not suggest that it's a fault only of the drivers. Because they would have had crashes in a similar way in other places they encounter congestion. This is not the only congested place in the Twin Cities. So we needed, in order to understand what happens, and this is an example of what traffic looked like until last Monday, by the way. Now it's shifted to the right. We have a very specific pattern here that is encountered in other places, but here is very extreme. You have a downstream entrance, the 35W northbound to 94 interchange, which is bringing a lot of traffic. And it's so much traffic that MnDOT doesn't dare meter it, because that cube will very quickly, as it actually does anyway, will spill on 35W in the middle of the road. So that's danger. It comes in and people merge in immediately on 94, causing the right lane to get congested. Now it's interesting that for the period that this queue is propagating from the merge point all the way to Portland Avenue, which is approximately 2,000 feet, virtually no crash happens. It is when that queue reaches this position here, this is the flyover ramp from freeway to freeway, and the bridge at the edge of the picture is Portland Avenue. This is when that reaches that point that all the crashes happened. 90% of the crashes happening there. The rest of the 10% is upstream from that point. So it wasn't an easy answer. We needed to collect detailed information in order to observe the crashes. Traditionally, crashes are rare. Traditionally, you cannot just go wait on a specific spot on a road with a camera at your hand and take a photo of the sequence of events that leads to a crash. Thank God that doesn't happen, except in this place. They're so often and they're so concentrated in a relatively small area that we can put a camera, and we did. This is a view from one of the high-rise buildings that it is outlining this area, and we put our own surveillance cameras there, and we put our own machine vision traffic detectors, otoscopes, and we had the ability to collect a complete video that describes the entire sequence of the event. And I'll show you more details about that in the, actually, I'll go now. So, as you see here, we have 3 cameras, and actually 2 of them are a machine vision sensor that gives us seamless video coverage of the queue from the point it starts at the merge and all its travel. And actually we have, as I'm going to say in the following slides, we have so much coverage that we can see the congestion spreading all the way to Riverside, which is more than close to 2 miles away. Because in 2002, when we established this, we didn't know what was going on. We just know that there was a very big concentration. Actually, me and Professor Davis, when we started this, we hypothesized, okay, MnDOT collects crash statistics in quarters of a mile. They don't pinpoint it in higher definition. So we looked at the statistics, and our hypothesis was that all the crashes would happen at the upstream merge area of 35W southbound 294 west. Because you have all this huge traffic coming in, they have an auxiliary lane to mix in. That's where we thought that all the crashes happen. That's why we found 2 rooftops around that area to look at it. Later on, we realized that, okay, well, now that we're watching the video, that's not where we thought they were happening. They're actually happening in another very specific spot. That was not a merge area, because the crashes happen after the lanes have been dropped to 3. Normally, crashes happen when vehicles change lanes and they butt to each other and there's friction. But that wasn't the case. That was the case after, it's almost 700 feet after you have started nice 3-lane, the 4th lane has gone away, that the crashes are happening. So there were other reasons. And when we watched this data a lot, basically we realized that there is a complicated mechanism there that generates these conditions. That was the impetus and this curiosity and these research questions is what created the original A94 field laboratory, which basically is comprised by 3 high-rise building rooftops where we placed our equipment. And from that, we had a continuous coverage, video coverage, seamless video coverage from 3rd Avenue all the way to Riverside. Now, in collaboration with MnDOT, we had access to MnDOT cameras. So every box that you see in these 2 pictures is an area that is covered with either our own fixed surveillance cameras or a camera that is owned by MnDOT. The blue ones, blue, green, yellow, are the ones that are the University of Minnesota cameras, and the red ones are the RTMC cameras. Back then, the best sensor that we had that could give individual vehicle measurements and speeds was otoscope. Back then, there was no Wavetronics radar yet, and the loop detectors give you aggregate. And since they're single loop detectors, they don't give you an estimate of, we only give you an estimate of speed, but not an accurate speed measurement. So what we did is we deployed the otoscopes, and we pointed them to the area upstream of where the crashes were happening. Downstream. So we wanted to look at the traffic conditions that precede the crash, because congestion moves backwards. And we put more sensors in individual places. Now, these sensors are, back then it was cutting edge, in some places still is, but they give you spot measurements. You get a measurement of the vehicle speed, but you don't know if that vehicle was accelerating when that speed was measured, or decelerating when that speed was measured, or doing something else. So with these measurements, and we specified them into specific areas, we developed a Q warning algorithm. Now, it took many, many years, and this is a little video about that. It took many, many years for the Minnesota Traffic Observatory, with the help of MnDOT, to actually implement the Q warning system. So it actually happened at the same time the RSI project happened and became a part of it. So right now, for the last 2 years and until last Monday, unfortunately, timeliness, we have those 2 otoscope sensors are sending real-time data to a computer at the Minnesota Traffic Observatory. That computer runs our infrastructure-based Q warning system, and it is called infrastructure-based because the way to communicate the message of the Q is through the infrastructure. So what happens is that computer generates a crash probability, and through an algorithm, it decides if it should raise the alarm or not. If the alarm is supposed to be raised, it sends a message to IRIS, the traffic operating system of MnDOT at the Regional Traffic Management Center, and IRIS activates the 2 upstream intelligent lane control signs that existed until last Monday. They were removed. And I will come to that why in a soon one. So what happens is, what you see on this picture is, this is the program that it calculates every 2 seconds the probability of a crash. And that probability is this blue line. It's fed to an algorithm that takes that and other things into account and decides every 2 seconds if it should raise the alarm or not. And if the alarm is raised, this is the farthest upstream sign that doesn't exist anymore. That's the sign on 11th Street overpass. And there's a second one that you see just below the letters, which is the signs on Park Avenue, that those still exist. And when that happens, a slow warning, slow speed ahead is activated and stays activated for as long as the system thinks that the drivers need to be warned. If the road recovers and speed picks up again, there's no need. If the congestion worsens and has passed this point, it also shuts down, because there's no point of warning anybody if they're going at 20 miles an hour already. So this system, in the first 3 months, and it's a very little amount of data that we have analyzed so far, in the first 3 months it showed a 22% reduction in crashes. There's a lot of cases where the sign was up and people like Hennepin County Sheriff still had a crash. Where were they looking? Anyway, but it shows promise. But this, as I said, is an infrastructure-based approach. It is limited because it depends on point detectors that only look at this location. So if you have another more traditional location where the problem is not so localized, you would have to have sensors everywhere. Well, in the past, this was a dream, but in the past that was a dream. Now this is actually already happening, and we call it connected vehicles. And basically, connected vehicles are vehicles that are providing to other vehicles, and whoever listens, essentially us, their location 10 times a second. They are sending out what's called the basic safety message, which is their location, their speed, their heading, the yaw rate, the wiper status, a lot of things to anybody that listens. So this technology has been developed now by the federal government and other countries in the world. And there's wonderful applications like the emergency electronic braking system, where your vehicle is listening to the 5th or 10th vehicle ahead of you, which there's no point of you as a human to ever be able to see. And if it sees that that vehicle comes to a sudden deceleration, it alerts you. If it's autonomous, it will actually hit the brake for you too. That would basically be the end of rear-end collisions. There is no way that anybody who sees a big flashing, beeping system in its dashboard, knowing collision imminent, not gonna take action. So, but the development of these systems require connected vehicles. Emergency electronic braking requires that all the vehicles in front of you are transmitting their location. In order to develop the algorithms for your vehicle responding and not beeping everything whenever another vehicle on another lane or something else does something, doesn't happen, we need to test it. We need data. Which brought us, with the help of Professor Donath, to decide to elevate this wonderful place for research to cover the needs of research in connected vehicles by upgrading our data collection capability with high-resolution sensors that can extract the trajectory of vehicles on the road, not just measure their speed at one location. Professor Davis has spent years analyzing manually video collected from this site, because when you do it with video, if you want to do it at the resolution necessary, it takes a very long time. So we have a few tenths of trajectory sets from crashes, as I say, we had, that were extracted that way, but it's definitely not a way that you can learn something. You need to observe for a long time. So that was the goal for the Connected Vehicle and Traffic Safety Research Laboratory, so no, changing the name, was to collect the high-resolution vehicle trajectory data from a significant length stretch of highway. So not just a small part, as big part as we can. And we would like to make this data available in real time, so not only are good for research, but are good for testing applications in actual connected vehicles that are in that area. So there is a feedback. So there are applications that have been developed by the federal government that are depending on vehicle-to-vehicle communication. There's also applications that are developed with the help of the federal government that depend on vehicle-to-infrastructure communication. So vehicle-to-infrastructure, you don't need to have all the vehicles instrumented, because you receive the trajectories from some parts of the fleet that are instrumented, and from that you infer with greater accuracy what are the patterns, what are the dangers, and you alert vehicles upstream, either with in-vehicle messages or with variable message signs. But in order to have that accuracy, you need to follow these vehicles to look at their deceleration pattern, the deceleration rate, everything. Even those few connected vehicles, we don't have. The biggest number that you can find of them is right now in Michigan, in Ann Arbor. And even there, it's about, 3% of the entire fleet of the city. And they don't have a place like this. So we needed to have a laboratory that could collect data, but also to communicate this data to people who are experimenting and developing things and testing them. So this is another video that shows very similar things than the previous video, but now it focuses on the new things. So our laboratory, the Minnesota Traffic Observatory, is directly connected with 3 rooftops This is the 3rd Avenue rooftop. This is the Augustana or 11th Avenue rooftop. And the last one is on Cedar Avenue, the high-rise building. That was the original rooftops. But these rooftops also give us wireless connectivity to the entire stretch of the road. So we have our cameras. So as I said, this video overlaps a little bit with the other video that have seamless video coverage of the entire area. Q. We have to perfect the timing a little bit better. Go on. Do I dare to fast forward? No, okay. Did I screw it up? Go. Okay. So, the new thing now is that in actually 1, 2, 3, 4, 5 locations, we have placed these high-resolution radar sensors that cover the area from Chicago Avenue overpass all the way to halfway the 3rd Avenue overpass. This is 2/3 of a mile distance. And basically what we have in that space, we have almost continuous coverage of collection of trajectories of practically anything that moves on that road. And we have also placed dedicated cameras on each one of those radars, so we can actually get a real-time verification of their accuracy and data. So they're not perfect. I'm not going to stand here and say that they're perfect, but it is an amazing amount of data that we have. This system has been online for more than a year now, and it is collecting data. Half of it is collecting data 24/7 because it is powered from regular power. The other one is solar, so I'll explain. So all the stations are synchronized with GPS clocks. So every piece of data, every piece of trajectory that is collected at 20 Hertz is time-stamped at a clock that it is as perfectly synchronized with all the other stations as you can get, because they're all getting their time from GPS satellites. And they transmit this information in real time back to our laboratory. The backhaul of communication is that we have, from the MTO, we have a fiber optic connection to the rooftop of Moose Tower across the street on Washington Avenue, where we have our 5 gigahertz point-to-point radio link and to 3rd Avenue, and from there we connect to the other ones. You would say, why did you go the long way and then you came back? Because Cedar Towers are in the way. So from the other places you cannot see Moose Tower. So that basically makes these three rooftops and part of the university network. From this, now we have another set of radios. These are multi-purpose point radios. So we have a sector antenna on 3rd Avenue that is covering the entire stretch of the I-94 Commons, allowing all the sensors to be able to be, our network is extended all the way to the actual sensor location. So these white boxes here, that is the radio. The black boxes are the radar sensors. Specifically, and the first one that we deployed, guess when? Last winter. Well, actually, it was the winter before last. But anyway, is on 3rd Avenue. This is a Mindot ITS pole. It's a Mindot pole that has a Wavetronics radar on it and sometimes a camera. We developed our own equipment. So our equipment is actually latched on with magnets on the pole. And the only thing it takes from the Mindot cabinet is power. So we made a promise long time ago to Mindot that we're not gonna be going into the right of way unless we have to, and we're not gonna touch their network or any of their information pipelines because of security reasons. So we're getting power, and from that we have the radar and a camera. Now, the goal was to have seamless trajectories. So we couldn't jump to the next convenient Mindot location. We had to put sensors where they needed to be. Unfortunately, where they needed to be, there was no power. And our funding did not allow hiring a contractor to dig ditches and install power. That's out of the question. I mean, we are still a university, not the federal government. So what we do when we have a problem, we'll solve it. We'll solve it any way we can. So we, and specifically our lab manager, Gordon Parik, and our other former and current employees, developed a solar-powered radar and radio station. Basically, we hired Egan Electric to put a wooden pole where Mindot allowed us to put it behind the guardrail, so there's no problem. So this is the Portland Avenue Bridge. And in this box, which was actually donated by the Intelligent Vehicle Laboratory a couple of years ago, we have car batteries and a solar controller. We actually over-designed it. It hasn't lost power at all. Snow, rain, only half a day it gets sun because the bridge is in the way. It hasn't lost power. It recharges the batteries enough during the day to keep going. And it has 2 radar stations. One radar station is looking towards the west to pick up what the radar station on the 3rd Avenue pole, which is on the other side of the bridge, doesn't see. And it has a short-range radar station to see underneath the bridge. These radar sensors, because of echo, because they're Doppler radar, when they're far, the bridge forms a barrier. And even if visually you can see underneath the bridge, the radar doesn't get detection. But if you are already under the bridge, then it's fine. On the other end, we have again a solar station. This is the Park Avenue Bridge that now the radar is looking west. The previous station is over there. So we have crossing detection. So at the farthest end of each of the radar stations, we have overlapping sections. On the other end, on the other side of the Park Avenue Bridge, is the Park Avenue gantry, Intelligent Lane Control Sign gantry, where MnDOT allowed us to mount two sensors. One sensor, and the two here only because we were experimenting at that time, there's only one normally, is right in the middle above the road, pointing straight east, and it sees as far as Chicago Avenue Bridge. And the other sensor is on the pillar on the south side of the gantry that looks underneath the bridge to close the connection with the sensor that's on the other side of the bridge, the solar station. So from Chicago Avenue overpass all the way Park, Portland, 65 flyover to the other end, close to 3rd Avenue, we have a complete coverage and we're collecting trajectories. These field stations were developed by us. These are Pi computers because they are very simple to program, extremely cheap, and they consume very little energy. So I cannot tell you too much details about the Pis because they're the babies of Gordon. But as I said, they have a GPS clock for time synchronization. They are running a radar driver that was developed by Brian Davis, based on code that was developed a long time ago by the Intelligent Vehicle Laboratory for the CICAS project. So we were, thank you very much for sharing the code and saving us trouble, because it's a very good library of functions. Basically what it does, it is running a driver similar to the driver that you have on your computer for your mouse, for whatever, that connects to that sensor and brings the data to this little computer. There they're checked. If the communication to the station is by some reason disrupted, because the wireless link goes down, the power on the rooftop goes down, some reason, these little Pis have the ability to keep collecting data for, I don't know, a couple of days worth of measurements. And the timestamp is added at this point based on the GPS sensor. So initially we tried to just send the data back. But we're talking about a lot of sensors and a lot of data. There's 85,000 vehicles a day passing that location. We're tracking every move they make 20 times a second for 2/3 of a mile. Radio communication, any kind of network communication has delays. The radars don't have a clock, so the data originally as they're collected are not time-stamped. And if they were time-stamped, because it would be the clock of that particular sensor, you cannot synchronize them perfectly. So if we were receiving the data, they would have an unknown amount of delay on the different hops from one radio to another, to another, to another, to our server at the MTO. And their timeliness would not be able to be guaranteed. So the solution was to put the timestamp in the most synchronized and accurate way that we can think of, other than an atomic clock, I suppose, and put it as close to the sensor where the data are collected as possible. So from that point on, when the data is delivered finally to the database server, it doesn't make any much difference other than sub-second real-time applications because they're already in the right order. The radar that we're currently using are 24 gigahertz infrastructure approved radar manufactured by Smart Microwave Sensors in Germany. They are not the latest and greatest radar that you can get. They were when we bought them, but of course that was 2 years ago, so they're not anymore. But we're using different types of sensors because with this radar, if you want to have distance, you're giving away width of coverage. And again, if you want to see more, closer, you're giving away distance. So there are different antennas, essentially, that are forming the beam, and we selected them to cover exactly the parts that we needed. These are some information about the operation of the radar. The accuracy that they have is 0.1 miles per hour. That means because they're Doppler radar, they're only seeing things that move. And they need to be moving with at least 0.1 miles per hour in order to be visible. And if two objects are moving with exactly the same speed down to 0.1 miles per hour, the radar will think it's the same object. The newer version of this radar actually has multiple sensors on the same box, so it can actually differentiate targets with elevation and azimuth. And we're hoping that with the new support that we're getting from MinDOT, we'll be able to get those. I'll jump this. Now, we're getting deeper into the system architecture. As I said, at the field near the sensor is where we have the driver connected to the sensor, and it receives the data through a serial connection to the sensor. So it's hardwired. At this point, we have the timestamp being added, and if the communication channel is open and everything is fine, this information then is transmitted to two places. The IPC, what the IPC stands for?
Inter-process communication.
Thank you. Inter-process communication server that receives the information and will deliver it to applications that need it at that point. And there is one direct client that receives this information, serving specifically the I-94 data server at the MTO, which saves the information. Need to be done. Okay. I thought I had another 10 minutes. So the data, the way that the system works, the data are present in real time, updating. So anybody who uses the API that we have changed from the original Intelligent Vehicle API can link their application and receive this data as they come, but also they are supplied to two applications that we have right now: speed harmonization, which is the inflow speed harmonization and inflow queue warning algorithms developed by the federal government that receive this information as if they were coming from connected vehicles, and a visualization program that we have developed. I'm not going to go into too much detail on the driver, not the server, other than to say that it can receive data and save it if there are any issues with communication. If you run the visualizer in real time, and we need to put a map on this one, but basically you will see the targets moving, and since at this point the data is not filtered in any way, you will see double targets in some cases when two radar are detecting the same object. This photo was taken before they were perfectly calibrated. Now they're overlapping each other. The client, as I said, it reads the data, it checks a few things, and then it puts the information on the server. The server, which now has how many petabytes of peta number of records? The records are not big because it's just 3 speeds and the displacement, but they're 20 hertz. Basically are saved in a Postgres SQL database that has an architecture that we developed, making retaining the individuality of every sensor, so the data even at this level is unfiltered, but allows subsequent duplication of filtered data. So we don't want to lose any of the original collected information, even if we run applications that are cleaning them up and stitching the trajectories and generating better information. There are a number of tools that are written in Python that are reading the real-time or historical data from the database and can provide them to anybody who has use for it. And we run, as I said, we're running the two control algorithms. We have an offline database visualizer, so if you want to work with the data that are saved in the database, you have the ability to query the database for a specific time, an instance, location, lane that you're looking at, and it will retain you the trajectories that were collected at that location and plot them, and you can play with time and look at the progression or look at all the data. So this is where we are right now, and we're looking for users. I've been advertising what we have because it's a great piece of source of information, the highest resolution of traffic data that I can think of at such a large quantity. There's a lot of research that can be done with it. Now, one future research plan that was very recently being funded by MnDOT is to extend the I-94 Minnesota queue warning algorithm upstream to Cedar Avenue. The reason we're going to be doing that is because where the two downstream stations, the 3rd Avenue and the Portland Avenue stations are right now, very, very soon will be a big hole in the ground for the next 4 years. So we will have to remove them, but now we have the support to move them upstream and keep our coverage just outside of the construction zone. Yes, we would like to keep them in the construction zone, but that's uncertain. We're still going to have all our sensors on the rooftops overlooking at the construction zone, so we're still going to have point measurements, but the radar have to be out. So hopefully in 2 years from now, we'll be able to present results of a Q-warning system working for an entire year based on high-resolution data. And if by then we have connected vehicles, we can actually send the information directly to them. And that's what I have.
We don't have a lot of time left during the seminar slot.
Sorry.
So I was hoping we'd have a few more minutes for questions.
I get carried
We
away.
can entertain one or two. Are there any offline? No? Any questions, please?
I have a couple points here. What was the percentage of reduction?
22%.
22% in the 3 months that you?
3 months, yes. 56 days to be exact.
Okay.
It's 3 months calendar time, but it's only Monday, Tuesday, Wednesday.
Yeah. And not to discredit who I work for, but when you said in your earlier part of the presentation, it's DPS that actually assigns the reference points to these crashes, not MnDOT. MnDOT has the method to go in and correct them, but
Okay.
it's only done if it's being looked
Then
at.
apologies to Mindut.
Yeah.
Anybody from DPS here? No? Okay, good.
Raj?
John, is this data available online for?
Online, no, because that would require for us to create web-based tools to access the data. But they're in such numbers that it's better that you ask and we give you a hard drive.
Okay. So we can get the data to, if you want to do some analysis or estimate.
Yeah, I mean, the video data are sort of available online. So, because you need the video to know what's going on, because if you go looking for something in the trajectory data, it's like looking like a needle in a haystack.
Anyway, we're running out of time, so please talk to John afterwards. Just want to remind everybody that next week we have the next seminar in the series, and we're going to have Professor Ray Benekahal from the University of Illinois at Urbana-Champaign, who'll be talking about railroad grade crossings, accident prediction models, and adjustments for historical data. Same time, same place, also on the web. But we're always happy to see you here in the room to enjoy the seminar eyeball to eyeball. So anyway, we'll see you next week. And the Traffic and Safety Council meeting will now begin, and I'm not sure who's in charge of that meeting. But thank you all for coming, and there's still refreshments in the back of the room. Thank you.
Is the idea that trajectory gets converted to a 2735 message instead of so far? Is that?
Yes. That's the idea. Okay. Not a complete basic safety message,
Right.
because we don't know all the details, but lateral and longitudinal placement and speed. Yes.
Oh, sorry, you can't see the data. The camp, partnership. And they are looking for